All right, welcome. We are going to talk about volume by shells, and we're going to do a couple examples. And the first thing to know is, why do we use volume by shells instead of disk and washer? Well, basically we want to use this method when disk or washer is almost impossible or pretty hard to use, or end up having lots of little pieces and holes in it. So we want to use it when disk and washer method is hard, as in we have to solve functions in terms of another variable, or it's virtually impossible. Second time we want to use it is when the cross sections are going to be taken parallel. Well, cross sections that are taken are going to be parallel to that axis of revolution. All right. So I think the best way, let's review first. If we have just a small cylinder, and so here's our little picture. So if we want to take the surface area of that cylinder, we know that, so think about the outside of a water bottle or a soup can, the label of a soup can. If we cut it right on its side and then lay it out, it's a rectangle. We know that its one length is 2 pi r, that's the circumference, where r right there goes from that axis, and then the height right there is just that height of the slice. And so our surface area, 2 pi r times h. Now, to remember, that axis of revolution is going to define, or that axis of rotation is going to define what our r is. All right, so let's do an example. We have y equals x squared. It's bound, so the shape is bounded by y equals x squared and the x-axis, which is also y equals 0. We also are going to bound that shape by 1 and 3, and we're going to revolve it, or it's going to be revolved around the y-axis. Drawing a picture, we have our y-axis and our x-axis. So here's our shape, starting at 0, but we're going to bound it by 1 to 3. Do a little shading. All right, our image is going to be on the opposite side of the y-axis. And so that's what that image is going to be. So if we take our slice, right there, that's a dx slice, and then we rotate that slice. Should probably go and rotate the other way, but that's all right. It's going to rotate around the y-axis. Gives us that cylinder. The r goes from the axis of rotation. Our height is going to be from that x-axis and to the curve y equals x squared. And so the surface area of that one green cylinder, oops, gotta spell cylinder right. So the surface area of that one green cylinder that's formed by that one slice is going to be 2 pi r times h. Our r here from the axis of revolution is x, and our height of that one green slice, or now green-red, is x squared. And we're going to add all those slices together from 1 to 3, bring out that constant 2 pi, there's our r, x squared times dx, our little thickness. Okay. Now, let's suppose we take that same problem, y equals x squared, and if we try to do it by the disk and washer method, our slices are going to be now in terms of dy. So our slices here are dy. And our shape, or our volume by revolution, we would have constant little r and big R for a portion of our solid. So look up here. So we're going to draw it in yellow. That portion is going to have a constant small r and a constant big R. But then for the remaining, or the rest of the shape, from, once we start right here and end up here, all right, our little r is going to change with respect to our function. Now, big R will always be 3, but little r will change with respect to our function. So it just makes this disk and washer method a little more difficult. So in this case, obviously shells, our shell method is going to be easier. Just since we're revolving around the y-axis here, which is parallel to our slices with the shell method, we're going to keep that the same. And the shell method is much easier.